Hello everyone, my name is Trần Đức Thiện. I'm from Ho Chi Minh University Technology Education. So today I'm very happy to stay here in the Asian Control Conference. So the topic I want to present today is Reprieve Performance, Adaptive Fault Tolerant Control for the Manipulator. The group author is Trần Đức Thiện and Nguyễn Thiện Quang. About my information, I received a bachelor and master degree in Department of Electrical and Electronic Engineering, Ho Chi Minh University Technology, Vietnam 2010 and 2013. The PhD degree from the University of Busan in 2020. Now I work as the lecturer and advisor of the Robotic and Intelligent Control Lab with the Department of Automatic Control, Ho Chi Minh University Technology Education, Vietnam. And my research interest is robotic manipulator, mobile robots, variable stiffness system, disturbance observer, nonlinear control, adaptive control, and intelligent technique. The content of my presentation is divided into the 5 parts. The first one is an introduction, the second is problem formulation and preliminary. The third one is the required performance of fault control, and the fourth one is the numerical simulation. And finally is some conclusion. Now we go to the introduction. Nowadays, robot has been applied in many areas, such as the automotive, medicines, ministries, industrial. In order to control the manipulator, so we have to face many challenges. The first one is the input constraint, state constraint, modeling error, disturbance, linearity, dynamic. In order to overcome this challenge, some of the closed-loop controls such as the model-based feedback control, adaptive control, sliding mode control, and backstepping control has been proposed. In modern industrial applications, the fault frequently occurs in systems that operate in a long-term operation condition. So it's necessary to consider the fault-tolerant control in the control design to ensure that the system works safely. The main goal of the fault-tolerant control design is to maintain the performance and stability of the control system in the presence of the fault. The fault-tolerant controls can be classified into the passive and active fault-tolerant control. For the passive fault-tolerant control, the approach is developed based on the robustness of the conventional control without any feedback of the normal and fault operation. In contrast, the active fault-tolerant control depends on the online results of the fault diagnosis observer to make the decision for the reconfiguring the control structure. Although the active fault-tolerant control possesses a complex structure, it can manage the high magnitude fault well. This paper is proposed an adaptive fault-tolerant control for the tracking accuracies and satisfaction of the output response with the prescribed performance of an uncertain manipulator with the actuator fault. In order to manage the prescribed performance requirement, a transformation technique is applied to integrate this requirement into the manipulator dynamic by creating a new dynamic. Then the robot control is designed based on the new model with the backstepping techniques, the steady state observer, and the fuzzy logic system. The steady state observer has to approximate the known uncertainty, including the external disturbance and actuator fault. In practice, the approximation error of the steady state observer in the changing state is significant. It can destroy the control performance. In order to overcome this challenge, the fuzzy logic system is applied to compensate the error. Finally, some simulation of the two UF manipulator are implemented in the bottom simulator to prove the effectiveness of the robot control. Now we move to the section 2, In the section 2, we present the manipulator dynamic by the equation 1, and dt is the uncertainty including the modeling error and external disturbance. The actuator flow is presented by the equation 2 is including the bias, error, and losing effectiveness. In order to integrate the actuator flow in the control design, the manipulator dynamic in the equation 1 is represented by the equation 3. So we have a delta dt including the uncertainties and bias, error, and losing effectiveness errors in the actuator flow. We have three assumptions for our manipulator. Assumption 1, the manipulator is constructed thus for any actuator failed at the lock-in phase. The remaining active proportions of the order is available, then the manipulator still be controllable. Assumption 2, the reference chances and its time derivatives are the continuous and bounded. Assumption 3, for the non-disturbance, delta D including the external disturbance and actuator flow, there exists an uncertain non-negative smooth function is presented by the equation 4, and non-disturbance in the manipulator are approximated by recursive linear system. About the steady state observer, the steady state observer is used to estimate the number uncertainty, and extra state it trees is provided to exhibit the number uncertainty. In order to design this observer, so we have to present the manipulator dynamic in the state-space model as presented in the equation 6. We have assumption 4 for our manipulator. The first one is based on the assumption 1 and remark 1. The number uncertainty are bounded. Additionally, the time derivative of the state 3 is also assumed to be bounded. So the steady state observer is presented by the equation 7. The fuzzy logic system is selected in the recursive linear system. So it's designed how to satisfy the conditions A, and the fuzzy logic system is used to compute the auxiliary signal in the Jensen states when the steady state observer does not operate effectiveness. The refined performance approach can be explained as the follows. The control will apply to the manipulator and guarantees that the output response is tracked to the reference and stay in the upper boundary and lower boundary. The refined performance is described by the condition 10 and 11. So we define the new error variable yes I to interact the refined performance into our dynamic. So the unconstrained dynamic of the manipulator is presented by the equation 14. Now we move to the section 3, robot controller. In the robot controller, it develops based on the backstepping control, steady state observer, fuzzy logic system, and adaptive law. Where for the unconstrained manipulator dynamic, when the backstepping approach is conducted in a robust manipulator, the output response will stay in the refined response. The steady state observer is employed to approximate the non-disturbance, including the uncertainty and actuator flow. The adaptive fuzzy logic system is compensate the approximation error of the steady state observer in the Jensen state. The effectiveness of the steady state observer and adaptive fuzzy logic system to ensure the reliability and quality of the control system. The robot controller is conducted as the follows. The first one, we define the tracking error as the equation 17, and next is select the virtual control as the equation 18, and the controller is selected by equations 19, and in the controller we can see is the result of the extended state observer is3 hash, and the result of the fuzzy logic system is presented by equation 20. In order to verify the effectiveness of robot controller, some simulations are implemented on the 2DOF manipulator with the existence of the external disturbance and actuator for in the 13 seconds. The simulation environment in the Model Simulink 2021A with the sample time is the 1 millisecond. The friction model applies in the manipulator are the viscous and static friction, which is expressed by equation 28, and the trajectory is referenced in the choice space. The scene signal is presented by equation 29, and the flow in the manipulator is the bias flow, and losing effectiveness is presented by the equation 13 and 31. About the fuzzy logic system, we use the Gaussian functions for the membership function. Is presented by the equation 22, and we have equation 23. The fuzzy set are selected intervals from the -5 to 5, and inertial condition of the choice 1 and choice 2 is pi 6 and pi 6 radian. And the parameter of the dynamic for the manipulator is presented in the paper 14 in the reference. The figure 2 is presented for the reference response in the choice 1 and choice 2. The figure 3 is presented for the error response of the tree controller in the choice 1 and choice 2. You can see in the tree controller is the black line present for prescribed performance by stepping controller, blue line present the prescribed performance by stepping extended observer, red line present for the robot controller. So tree controller we consider prescribed performance requirements. So the output response of the tree controller is stay in the upper boundary and lower boundary. And in the second controller and the robot controller, you can see because we use extended state observer, so when the fault arises in the 5th second and 20 second, the accuracy of the system will still guaranteed. But in the first controller, we not use to extended state observer, so the control performance is degraded. Next, we compare the second controller with the robot controller. In the second controller, we can see in extended state observer, we call the approximation results in the num uncertainty of the extended state observer in the transition state from the 0 to 1. So is significant. So the accuracy is in the second controller is have not to approach to have an overshoot in overshoot, but in the robot controller we use a fuzzy logic system. So you can see it's in the choice 1 and choice 2, not the overshoot in the transition state. Figure 4 is the comparison between the disturbance and estimate its results from the steady state server into choice of the manipulator. You see, in the steady state, the estimated result is checked well to the disturbance in Taiwan and Taiwan, but in the transition state, it's not good. Transform a fuzzy logic system into choice. In the transition stage, the output of the fuzzy is increased very big to compensate the approximation error from the steady state observer. After that is the discrete varies quickly. And the figure 6 is present for adaptive gain response in the fuzzy logic system, and the figure 7 is present for control signal of the robot controller in the Taiwan and Taiwan. Based on the above reason, so we have a summary conclusion about our research. Firstly, this paper proposed the adaptive fault-tolerant control for manipulator, again actuator, failure, and external disturbance. The manipulator dynamic were presented, which the external disturbance and actuator fault comprise of the disturbance. The transformation techniques employed to interact the retrieve form into the manipulator dynamic. Robot control is developed based on the backstepping technique, standard state server, fuzzy logic system, and adaptive law. The backstepping approach within the robot controller have to ensure the stability of new dynamic. The standard state observer is used to approximate the non-disturbance. In addition, the adaptive fuzzy logic system is compensated for the estimation error to enhance stability, robustness, and reliability. And finally, some simulations are conducted in UDF manipulator to verify the superiority of the robot controller. So, thank you very much for your listening.